In this video, I'll just briefly summarize what we learned from lecture 7, 8 and 9. Okay? Lecture 7, we briefly go through the alliancing issue, and we say that even if you have a 0th order hole, right, you also need a times 2 frequency because you have a phase shift. Your original is something like this. Your digital signal is after your 0th order hole, it has a phase shift that is lagging behind. Alright, is it something like this? Yeah, something like this. So therefore you need to have a phase shift of times 2 in order to shift it to this particular same signal as your analog system. Okay, and the shifting is this times 2 shifting is actually called the emulation. Alright, so this is one way to emulate or to edit your signal. And the method of emulation by definitions is that you match or surpass your limitations, or in other words you reproduce the function or actions by a certain other stuff. Okay, so it's something like a copying or imitate something. Alright, in a very nice way we call this emulation. Okay, so we want to emulate or we want to reform our analog signal. Alright, so we want to imitate or copy our analog signal by using a digital one. Alright, so therefore this emulation is one method. The second method is we use the tasting method, or the trapezoidal way of doing things. Alright, we say that the most powerful one is actually the tasting or the bilinear or the trapezoidal. Alright, where you map all the stable S in the S domain. This is in the S domain. You map it all into the Z domain's stability zones. So everything is mapped over this side in the Z domain. Alright, using the tasting method. However, we have some distortion, so we use a pre-warping. Alright, we also discussed in the videos in the lecture 8. Alright, and the pre-warping is also another form of emulation. Also, tasting method is also of another form of emulation because you try to model your analog signal. So all along we have been trying is trying to model your analog signal or model your analog output. Alright, so you want your output because normally your digital output may have a little bit different from analog output, so you want it to be the same. So therefore you need this methods to emulate your stuff. Okay, so these things comes in. In this series of lecture 9, we talk about pole zero match. Alright, is another way of emulation. Alright, to model your digital in terms of the analog. Alright, and the last one which is just a few videos, two videos ago, talk about 0th order hole, which is a discrete design. Alright, because you want to hold discretely of every discrete samples, some different samples that you take, you're gonna hold it discretely and do things like this. So this is in terms of the discrete design. But nonetheless, all this is a digital controller. Alright, you are so far designing your digital controller, alright, either by emulation, by copying, and ensuring that it is the same as your analog. Alright, so you need to always compare with your analog and ensure that your digital must be equals to your analog with the same input frequency and the same transfer function. Your digital must be equals to analog, otherwise something is wrong. You need to emulate. And in order to emulate, one way is to alliancing effect, or you need to prevent the alliancing, you need to times 2. Second way is to use the tasting method. Third way is to use the pole zero match. Alright, things like that. Alright, this is only to prevent alliancing for this part. As for the modeling of your analog and digital, alright, because the digital domain has distortion, so therefore in order to model and prevent the distortion, you need to use either the tasting method or the pole zero match method. Okay, and nonetheless, you can also use the 0th order whole discrete design together with the emulation times 2 of the frequency, things like that. Alright, so I hope that this is pretty clear so far all along, and you are so far designing a digital controller. Alright, these are all the basics to designing a digital controller. So therefore I think this is it for the whole summary. Alright, and yeah.